September 25, 1998, 11:30 a.m. Esso Longford Gas Plant, Victoria, Australia. John Lowry, 52 years old, senior operations engineer, stood in the control room watching pressure gauges climb as Plant 1 came back online after routine maintenance. The restart was proceeding normally, temperatures rising, pressures stabilizing, systems responding as expected. He'd supervised hundreds of restarts over his 28-year career at Longford. This one felt routine. Pumps running smooth, called out Peter Wilson, the shift supervisor, monitoring the heat exchanger that was warming the gas stream after its journey through the ultra-cold separation process. Temperatures coming up nicely, right on schedule. What John Lowry didn't know, what none of the 12 workers at the Longford facility that Friday knew, was that the heat exchanger Peter Wilson was monitoring had developed a catastrophic flaw during the shutdown. A section of piping, brittle from years of exposure to cryogenic temperatures, had fractured. As warm hydrocarbon liquid flowed through the damaged exchanger, it was leaking into areas where it would flash instantly to vapor, creating explosive conditions that would within minutes kill 2 men and plunge the entire state of Victoria into an energy crisis. The irony was crushing. Longford was Australia's most critical gas facility, supplying approximately 67% of Victoria's gas needs, feeding power stations, heating homes, fueling industry. The plant processed natural gas from the Bass Strait offshore fields, separating it into commercial gas for distribution and extracting valuable liquid hydrocarbons. It was considered state-of-the-art, with multiple safety systems, experienced operators and a strong safety record. Esso, the facility's operator, part of ExxonMobil, one of the world's largest energy companies, prided itself on operational excellence. But excellence in routine operations doesn't prevent disaster when unusual conditions arise and decisions are made under production pressure without fully understanding risks. The sequence of events that would lead to explosion had begun 2 days earlier, on September 23. Plant 1, one of Longford's 2 main processing units, had been shut down for routine maintenance on a valve. The shutdown was planned, scheduled, normal. What wasn't normal was what the maintenance revealed. When technicians opened the heat exchanger system for inspection, they found more extensive corrosion than expected. The decision was made to extend the shutdown, to conduct more thorough repairs. This created pressure. The plant was losing production, Esso was losing revenue, and Victoria was relying on reduced gas supplies from Plant 2 alone. On September 24, repairs were completed, but the extended shutdown had consequences. The heat exchanger had been cold, not just cool but genuinely cold, well below zero for longer than usual. Moisture had accumulated, frozen, created ice in crevices. And the piping, subjected to years of thermal cycling between cryogenic cold and normal temperatures, had developed microfractures that weren't visible in standard inspections. The restart procedure for Plant 1 was straightforward in theory: slowly warm the cold equipment, gradually increase pressure, carefully monitor all systems as they came online, but slowly was relative. The procedure had time targets, stages that should be completed within certain hours to maintain schedule and minimize lost production. John Lowry was under implicit pressure to restart quickly. Not explicit orders to rush or skip steps, but organizational culture that valued operational efficiency, that rewarded getting units back online promptly, that treated extended downtime as management failure. The pressure was subtle but real: complete the restart on schedule, demonstrate competence, avoid questions about why it's taking longer than planned. At 11 a.m. on September 25, the restart reached a critical phase. The heat exchanger, a massive unit that warmed gas streams from -50 degrees Celsius to normal temperatures, was being brought online. Warm hydrocarbon liquid was being circulated through the exchanger to gradually heat it. This process required careful monitoring. Too fast and thermal shock could damage equipment, too slow, and the restart would fall behind schedule. The procedure called for monitoring the exchanger's temperature at multiple points, ensuring even heating, watching for any anomalies. But some temperature sensors were out of service, disabled during maintenance, not yet recalibrated. The operators were relying on fewer data points than ideal, interpolating temperatures based on incomplete information. At 11:23 a.m., John Lowry authorized increasing flow through the heat exchanger. The temperature readings looked acceptable, pressure was stable, everything seemed normal. What he couldn't see, what the limited instrumentation couldn't detect, was that sections of the exchanger were heating unevenly, creating thermal stresses on already weakened piping. At 11:30 a.m., a 6-inch diameter pipe inside the heat exchanger fractured. The pipe was carrying lean oil, a hydrocarbon liquid mixture at moderate pressure and temperature. When the pipe ruptured, lean oil sprayed into the exchanger's shell side, where it encountered surfaces at various temperatures. Some of the lean oil contacted cold surfaces and partially froze, creating a dangerous situation. But some contacted warmer areas and began vaporizing rapidly. The hydrocarbon vapor started accumulating in the exchanger and in connected piping, creating pressure. And crucially, the vapor began leaking through gaps in the exchanger's casing, escaping into the plant area. The control room instruments showed pressure rising in the heat exchanger system. John Lowry noticed immediately. "Peter, I'm seeing pressure spike on HE401, he called to the shift supervisor. "Check the field readings." Peter Wilson headed to the plant floor to inspect the heat exchanger directly. As he approached, he smelled hydrocarbons, the distinctive sweet odor of gas and oil. He saw white vapor venting from the exchanger area, forming a visible cloud. This was bad. This was very bad. "John, we've got a major leak." Peter radioed back to the control room. "I'm seeing vapor release from the exchanger. We need to shut down." John Lowry immediately initiated emergency shutdown procedures. But emergency shutdowns aren't instantaneous. Valves take time to close. Pumps take time to stop, and the vapor already released didn't disappear. It was accumulating around the exchanger, forming an invisible cloud of explosive hydrocarbon gas mixed with air. Hydrocarbon vapor is heavier than air. It doesn't disperse upward but flows downward, accumulating in low areas, filling valleys and depressions. The Longford plant area was relatively flat, but even small elevation changes concentrated the vapor. Within 2 minutes of the initial leak, an estimated 8–10 tons of hydrocarbon vapor had been released, creating a gas cloud covering approximately 2 hectares of the plant site. Peter Wilson, standing near the leaking exchanger, was in the heart of the vapor cloud. He radioed again. "It's getting worse. The whole exchanger area is filled with vapor. I'm evacuating." His transmission cut off at 11:32 a.m. At that moment the vapor cloud found ignition. The ignition source was never definitively identified, possibly an electrical spark from equipment, possibly a hot surface, possibly static electricity. With that much hydrocarbon vapor at explosive concentration, ignition was inevitable. The only question was when and where. The initial explosion occurred at the heat exchanger. The vapor cloud ignited, producing a massive fireball and pressure wave. The blast was equivalent to approximately 2 tons of TNT. Windows shattered in nearby buildings. The ground shook. Workers across the plant site were thrown down by the shockwave. Peter Wilson was at the epicenter. The explosion killed him instantly, the pressure wave and thermal pulse ensuring death in microseconds. His body was found later, burned beyond recognition, identifiable only by his position and equipment. The explosion ruptured additional piping and equipment, releasing more hydrocarbons, creating secondary fires. The entire heat exchanger area became an inferno, flames reaching 50 meters high, black smoke billowing across the plant site. In the control room, John Lowry felt the building shake. Alarms screamed, pressure alarms, fire alarms, shutdown alarms, every warning system activating simultaneously. He looked at the monitors showing plant cameras. The heat exchanger area was hidden behind flames and smoke. "All personnel evacuate," he shouted into the plant-wide radio. "This is not a drill. Full plant evacuation." The 12 workers at Longford that day began evacuating. But the plant site was large, approximately 50 hectares, and some workers were far from the exits. And the explosions weren't finished. At 11:34 a.m., a second explosion occurred. A storage vessel, damaged by the first blast and exposed to intense heat, ruptured catastrophically. This explosion was larger, approximately 3 tons of TNT equivalent. More piping ruptured. More fires ignited. The cascade was beginning. John Lowry and 3 other control room operators evacuated the building, running toward the main gate. Behind them they heard a third explosion, another vessel failing, another fireball rising into the sky. The entire plant was becoming an inferno. At 11:36 a.m., the most catastrophic failure occurred. A large storage sphere, a pressure vessel containing ethane at high pressure, was exposed to fire from the burning heat exchanger area. As the vessel heated, pressure inside increased. The vessel's relief valves opened, venting ethane to reduce pressure. But the vented ethane immediately ignited, creating a massive jet flame that heated the vessel even more. This created a feedback loop. Heating increased pressure triggered more venting created more flames caused more heating. The vessel was self-destroying, approaching the point where the metal would fail catastrophically. At 11:38 a.m., the ethane sphere experienced a BLEV, boiling liquid expanding vapor explosion. The vessel, containing approximately 60 tons of ethane, ruptured explosively. The blast was equivalent to approximately 8 tons of TNT. Fragments of the vessel, multi-ton pieces of metal, were hurled hundreds of meters. The fireball was visible from 50 kilometers away. One fragment, a section of the sphere weighing approximately 15 tons, traveled 300 meters before crashing into the plant's main pipeline manifold, rupturing multiple high-pressure pipelines. Another fragment destroyed a control building. The explosion's shockwave shattered windows in the town of Longford, 2 kilometers away. And crucially, the BLEV and subsequent pipeline ruptures severed Longford's connection to the Bass Strait gas fields. The plant wasn't just destroyed, it was completely cut off from its gas supply. Victoria's main source of natural gas had been eliminated in 6 minutes of cascading explosions. The evacuation continued desperately. Workers scattered across the plant site ran for the perimeter, away from the flames and explosions. Most made it out. But one worker, Roger Brown, 48, maintenance technician, was in the wrong place at the wrong time. Roger had been working in a shed near the ethane storage area when the first explosion occurred. He'd immediately started evacuating, but had to run past the ethane sphere to reach the nearest exit. He was approximately 80 meters from the sphere when the BLEV occurred. The explosion's pressure wave killed him instantly. His body was found 50 meters from where he'd been running, thrown by the blast. Cause of death: massive blunt trauma from overpressure. He'd been far enough from the fireball to avoid burning, but close enough to the explosion that the shock wave was lethal. 2 dead, Peter Wilson and Roger Brown. 10 survivors, some with minor injuries from falls or flying debris, and an entire gas plant destroyed. But the disaster's impact extended far beyond the plant site. Within hours, Victoria began experiencing the consequences of losing 67% of its gas supply. Power stations running on gas began shutting down, not immediately, as they had some reserve fuel, but within hours as supplies ran low. Industrial facilities dependent on gas shut down production lines. Hospitals activated emergency protocols. And as evening approached, Victorians turned on heating. September is late winter in Australia, and temperatures that night would drop to near freezing, only to find gas pressure dropping to unusable levels. By 8 p.m. on September 25, gas supply to Melbourne, Australia's second largest city, had effectively ceased. 2 million people had no gas for heating or cooking. Industries employing hundreds of thousands were offline. Power generation was reduced by 30%, forcing rolling blackouts across the state. The economic impact was immediate and catastrophic. Victorian industry lost an estimated $6 million per day in the immediate aftermath. Total economic impact over the 2 weeks until partial gas supply was restored exceeded $1.3 billion AUD. It remains one of the most expensive industrial accidents in Australian history, not in terms of lives lost but in economic disruption. The investigation began immediately. Multiple agencies were involved: Victorian state regulators, federal workplace safety authorities, Esso's internal investigators, and independent experts. The findings revealed a constellation of failures. The immediate cause, the pipe rupture in the heat exchanger, resulted from brittle fracture. The pipe had been subjected to years of thermal cycling between extreme cold and normal temperatures. The metal had become embrittled, developing microcracks that propagated over time. The extended shutdown, leaving the exchanger unusually cold for longer than normal, created additional stress. When warm liquid flowed through during restart, thermal shock completed the fracture. But why wasn't the embrittlement detected? Inspection procedures focused on corrosion and wear but didn't adequately assess brittleness in piping subjected to cryogenic temperatures. The inspection regime was designed for normal industrial piping, not for the extreme conditions at Longford. This was a systemic failure, the wrong inspection standards applied to unusual equipment. The restart procedure contributed to the disaster. The decision to bring the heat exchanger online with incomplete temperature monitoring was made under production pressure. John Lowry had authorization to proceed, and technically the procedure was being followed. But the procedure itself was inadequate for the conditions. It didn't account for equipment that had been cold longer than normal, didn't require complete instrumentation before restart, didn't mandate slower warming rates for extended shutdowns. The safety systems failed to prevent cascade. Once the initial leak occurred, the plant lacked systems to automatically isolate and shut down affected areas quickly enough to prevent explosion. The heat exchanger should have been able to be isolated instantly, venting safely contained, ignition sources eliminated. Instead, the shutdown took minutes, long enough for explosive vapor to accumulate and find ignition. The investigation identified what they termed latent conditions, organizational and systemic factors that created disaster preconditions. Esso's safety culture emphasized compliance with procedures, but didn't encourage questioning those procedures or stopping operations when unusual conditions arose. Workers felt pressure to maintain production, to complete tasks on schedule, to avoid delays. This created an environment where caution was discouraged subtly but effectively. Maintenance and inspection regimes hadn't kept pace with equipment aging. The Longford plant was 30 years old, operating beyond its original design life. As equipment aged, inspection intensity should have increased. Instead, it remained constant, creating an accumulating backlog of undetected deterioration. Engineering expertise had declined through downsizing. Esso had reduced staffing through the 1990s as part of efficiency initiatives. Experienced engineers who understood the plant's unusual systems retired or were laid off. Younger engineers lacked deep knowledge of the facility's specific risks. Institutional memory was lost, and with it, awareness of potential problems. Production pressure overrode safety considerations. Esso faced competitive pressure in the gas market. Every day of lost production cost money. This created implicit pressure to restart quickly, to minimize downtime, to keep gas flowing. The pressure wasn't explicit orders to compromise safety, but organizational culture that rewarded speed and penalized delays. The Royal Commission investigating the disaster concluded, the Longford explosion was not caused by a single failure or decision, but by an accumulation of latent organizational weaknesses that created conditions where disaster became not inevitable, but increasingly probable. The final trigger, the pipe rupture, was the last in a long chain of failures stretching back years. The accountability phase proved contentious and ultimately unsatisfying for many. Esso faced criminal charges for breaches of workplace safety regulations. In 2001, the company pleaded guilty to charges and was fined $2 million AUD, at the time, the largest workplace safety fine in Australian history. But no individuals faced criminal charges. Prosecutors determined that while poor decisions contributed to the disaster, no single person's actions met the threshold for criminal negligence. John Lowry, who'd authorized the restart, had followed procedures and acted reasonably given the information available. The procedures themselves were inadequate, but that was systemic failure, not individual culpability. This frustrated families of the dead, and many in the community. 2 men died because decisions were made incorrectly, because procedures were inadequate, because production pressure overrode caution. Yet no one was personally held accountable. The corporation paid a fine, significant but not crippling for a company with billions in revenue, and operations continued. The compensation provided to families was more substantial than in many disasters. Roger Brown's family received approximately $500,000 in workers' compensation and civil settlement. Peter Wilson's family received similar amounts. Not adequate compensation for a life, but more than the token payments victims' families received in many industrial disasters. The regulatory response was comprehensive. Victoria's workplace safety regulations were strengthened significantly. The Occupational Health and Safety Act 2004 created stricter requirements for major hazard facilities, required safety management systems, imposed higher penalties for violations and, crucially, created provisions for charging individuals, not just companies, with criminal negligence in workplace deaths. The gas industry specifically implemented new standards. Procedures for restart after extended shutdowns were revised, requiring more thorough equipment inspection, slower warming rates, complete instrumentation before proceeding. Inspection regimes for cryogenic piping were established, training for operators was enhanced. Esso rebuilt portions of the Longford facility with enhanced safety systems. The reconstruction took 2 years and cost over $100 million. When operations resumed, the plant had automated shutdown systems, improved monitoring, better isolation capabilities. The rebuilt facility was significantly safer than what it replaced, but the plant's importance to Victoria's energy supply didn't change. Even after the disaster, Longford remained critical infrastructure. This created ongoing tension. The facility that had catastrophically failed continued supplying most of Victoria's gas because no alternative existed. The state remained dependent on a facility that had proved vulnerable to catastrophic failure. This dependence illustrated a broader problem: critical infrastructure concentration. Victoria's gas supply was dangerously concentrated in a single facility. When that facility failed, the entire state suffered. The disaster prompted discussion of diversifying gas supply, building redundancy, reducing dependence on any single point of failure. Some diversification occurred, new pipelines from other gas fields, additional storage capacity, but Longford remains critically important decades later. The survivors carried trauma that never fully healed. John Lowry left the gas industry entirely, unable to face returning to work similar to what he'd been doing when 2 colleagues died. He suffered PTSD, experiencing nightmares and flashbacks. He blamed himself, despite investigations concluding he'd followed procedures and acted reasonably. "I authorized the restart," he said in later interviews. 2 men died because of decisions I made. Following procedures doesn't change that. The families of Peter Wilson and Roger Brown received compensation and apologies but not satisfaction. Peter's widow Margaret testified at the Royal Commission. "They tell me it was nobody's fault, that it was systemic failure. But systems don't make decisions, people do. Someone decided to restart quickly. Someone decided incomplete monitoring was acceptable. Someone decided production mattered more than caution. Those weren't systems, those were people, and 2 men died." Her testimony captured the fundamental frustration with how modern industrial disasters are understood and prosecuted. When failures are systemic, organizational, cultural, when disaster results from accumulation of small decisions and deferred maintenance and production pressure, rather than one obviously negligent act, accountability becomes diffuse. Everyone shares responsibility, which often means no one is truly held accountable. The Longford disaster transformed Australian industrial safety regulation and practice. It became a case study taught in engineering programs, a reference point for safety culture discussions, a catalyst for regulatory reform. The lessons learned about restart procedures, about cryogenic piping inspection, about production pressure, about aging equipment, saved lives in facilities across Australia and globally. But those lessons came at the price of 2 lives, at the cost of 2 weeks of economic crisis affecting millions, through a disaster that multiple investigations concluded was preventable with better procedures, better inspections, better organizational culture. The immediate aftermath of the Longford explosion revealed how critically Australia had underestimated infrastructure vulnerability. As Friday evening approached on September 25, Victorian government officials gathered in emergency meetings, confronting a crisis that had no precedent and no contingency plan. The state's gas supply, the fuel that heated homes, powered industries, and generated electricity, had effectively ceased to exist. Premier Jeff Kennett addressed the public at 7 p.m. "We are facing an unprecedented energy emergency. The Longford facility has been severely damaged. Gas supply to Victoria will be severely restricted for an indeterminate period. We are asking all Victorians to minimize gas and electricity usage. Businesses should prepare for possible closures. This is a situation we have never faced before." The The statement was remarkable for what it didn't say: that the government had no idea how long the crisis would last, that alternative gas supplies were minimal, that Victoria's economy might face weeks or months of disruption. The full scale of vulnerability was still being assessed. That first night, as temperatures dropped to 4 degrees Celsius, 2 million Melbourne residents found their gas heating inoperable. Some had electric heaters as backup, many didn't. Emergency shelters were opened across the city, community centres and schools where people without heating could find warmth. Thousands spent the night in these shelters, displaced not by natural disaster or war, but by industrial accident. Hospitals faced immediate crisis. Many medical procedures require gas sterilization equipment. Operating rooms use gas-heated systems. Food preparation for patients depends on gas cooking. Hospitals activated emergency plans designed for temporary gas disruptions lasting hours, not the weeks-long crisis they actually faced. Elective surgeries were postponed. Some procedures were relocated to hospitals in neighboring states. Critical care continued, but at reduced capacity. Industrial impact was even more severe. Victoria's manufacturing sector, automotive plants, food processing, chemical production, textiles, employed hundreds of thousands and contributed billions to the state economy. Most facilities depended on gas for process heat, steam generation, or direct fuel. Within 24 hours, approximately 60% of Victorian industry had shut down. Alcoa's aluminum smelter near Portland, one of the largest in the southern hemisphere, faced catastrophic risk. Aluminum smelting requires continuous operation. Shutting down allows the molten metal to solidify, destroying equipment worth hundreds of millions. The smelter operated its own gas supply from a separate field, but it depended on Longford's gas for supplemental supply during peak demand. Engineers worked frantically to maintain operation on reduced supply, balancing precariously between shutdown and continuation. The automotive industry faced immediate crisis. Ford, Toyota, and Holden operated major plants in Victoria, assembling vehicles and manufacturing components. These plants operated just-in-time manufacturing systems with minimal inventory, depending on continuous production to meet dealer demand. When plants shut down, the entire supply chain collapsed. Dealerships ran out of vehicles, suppliers laid off workers. The ripple effect spread beyond Victoria into national and international automotive networks. Electricity generation capacity dropped by approximately 30%. Gas-fired power stations supplying 1/3 of Victoria's electricity went offline or operated at reduced capacity. The state's coal-fired power stations increased output but couldn't fully compensate. Rolling blackouts became necessary, with different regions losing power for 2 and 4-hour periods to balance limited supply across the grid. These blackouts created cascading problems. Traffic lights failed, creating gridlock and accidents. Refrigeration failed, spoiling food in stores and homes. Computers and servers lost power, disrupting businesses and government services. Every blackout created more problems, more costs, more disruption. The economic hemorrhaging was extraordinary. Initial estimates suggested Victoria was losing $6 million per day in direct industrial production losses. But total economic impact, including business disruption, lost wages, spoiled inventory, emergency response costs, reduced consumer spending, pushed daily losses toward $50 million. By day 3, cumulative economic impact exceeded $150 million and was accelerating. Premier Kennett faced intense pressure. Opposition politicians demanded answers. How did the state become so dependent on a single facility? Why were there no backup supplies? What was the plan for recovery? The questions were valid, but they had no good answers. Victoria's energy infrastructure had evolved over decades with Longford as its centerpiece. No one had seriously considered what would happen if Longford failed catastrophically and simultaneously. Esso brought in engineers from around the world to assess damage and plan recovery. The initial assessment was devastating. The heat exchanger area was destroyed, multiple vessels ruptured, pipelines severed. Rebuilding would take months, possibly years. But Victoria couldn't wait months. The state needed gas immediately, or the economic damage would become permanent. Businesses would relocate, industries would collapse, the economy would spiral into depression. The solution required heroic engineering. Esso determined that Plant 2, which hadn't been damaged in the explosion, could be modified to increase output, partially compensating for Plant 1's destruction. But the modifications were extensive, installing new compressors, rerouting pipelines, modifying control systems. Work that would normally take months needed to happen in weeks. Round-the-clock construction began at Longford. Hundreds of workers, engineers, welders, electricians, technicians worked 12-hour shifts 7 days a week. The site became a 24-hour operation illuminated by floodlights, with helicopters ferrying equipment and supplies. The urgency was palpable. Every day's delay cost the state millions and pushed industries closer to permanent closure. Meanwhile, emergency gas supplies were being arranged. Pipeline connections to gas fields in other states were expedited. LNG, liquefied natural gas, was imported and vaporized to supplement supply. Every source of gas that could reach Victoria was exploited, regardless of cost. The state government essentially wrote blank checks: whatever it cost to increase gas supply, spend it. The alternative, extended economic collapse, was unacceptable. By October 2, 1 week after the explosion, partial gas supply was restored. Not full capacity, but enough for essential services and priority industries. Hospitals returned to normal operation. Power stations increased output, reducing blackouts. Some factories restarted production. The crisis began transitioning from emergency response to recovery and reconstruction. But the economic damage was already severe. Victorian GDP contracted by 1% in the fourth quarter of 1998, a significant decline directly attributable to Longford. Unemployment increased. Business confidence plummeted. The disaster's economic impact exceeded $1.3 billion AUD, making it one of Australia's costliest industrial accidents despite the relatively low death toll. The Royal Commission into the disaster began hearings in November 1998, chaired by former High Court Justice Dawson. Over 9 months, the Commission heard from 150 witnesses, reviewed thousands of documents, and conducted technical investigations into every aspect of the disaster. The final report, published in August 1999, was comprehensive, technical, and damning. The Commission identified the immediate technical cause, brittle fracture of piping in the heat exchanger, but emphasized that this was merely the triggering event. The real causes were organizational, cultural, and systemic. Esso's maintenance practices were found to be inadequate for aging equipment. The Commission noted, as the Longford plant aged, maintenance should have intensified. Instead, it remained constant or decreased due to cost pressures and staffing reductions. This created an accumulating deficit of deferred maintenance and undetected deterioration. Inspection regimes were inappropriate for cryogenic service. Standard industrial inspection methods weren't sufficient for piping subjected to extreme cold. The Commission recommended, specialized inspection protocols must be developed and implemented for equipment operating at cryogenic temperatures, with particular attention to embrittlement and fracture risk. The restart procedure was inadequate. The Commission found that the procedure didn't account for extended shutdowns, didn't require complete instrumentation before proceeding, and didn't mandate slower warming for equipment that had been unusually cold. The restart was conducted according to procedure, the report stated, but the procedure itself was deficient. Most significantly, the Commission identified what it termed cultural factors that created disaster preconditions. Esso's organizational culture, the Commission found, prioritized production over caution, rewarded operational efficiency over safety vigilance, and created implicit pressure to avoid delays and maintain schedules. The report quoted testimony from multiple Esso employees describing this culture. "You were expected to keep things running," one engineer testified. Shutdowns were seen as failures. There was always pressure to restart quickly, to minimize downtime. Nobody explicitly said compromise safety, but the message was clear: keep gas flowing. This finding that organizational culture, not individual negligence, created disaster conditions was revolutionary for Australian law. It suggested that corporations could be culpable even when no specific individuals acted negligently, that systemic failures could constitute corporate crime. The Commission made 50 recommendations addressing technical standards, inspection practices, restart procedures, safety management systems, and regulatory oversight. Most were implemented within years, transforming Australian industrial safety regulation. But the Commission's most controversial recommendation was criminal prosecution. The report stated, there is sufficient evidence to support charges against Esso under workplace safety legislation. The failures were not merely technical but represent serious breaches of duty of care that resulted in deaths. Esso was charged in 2000 with multiple breaches of the Occupational Health and Safety Act. The trial became a landmark case in Australian corporate criminal law. Prosecutors argued that Esso's organizational failures, inadequate maintenance, deficient procedures, production pressure, constituted criminal negligence even though no individuals acted with criminal intent. Esso's defense argued that the company had followed industry standards, that no one could have predicted the specific sequence of failures, that the disaster resulted from unforeseeable technical problems rather than criminal negligence. The company emphasized its safety record, decades without major incidents, and argued that one accident, however tragic, didn't prove criminal conduct. The trial lasted months, featuring technical testimony from engineering experts, organizational psychologists, and safety specialists. The jury heard about embrittlement, thermal stress, maintenance deferrals, restart procedures, and corporate culture. It was one of the most technically complex criminal trials in Australian history. In May 2001, Esso pleaded guilty to 5 charges. The company accepted that its systems and procedures had been inadequate, that failures to properly maintain and inspect equipment had contributed to the disaster, and that its safety management systems hadn't prevented foreseeable risks. The court fined Esso $2 million AUD, at the time the largest workplace safety fine in Australian history. But the penalty was controversial. Critics argued that $2 million was insignificant for a company with billions in revenue, that the fine wouldn't deter future negligence, that corporations needed to face penalties severe enough to impact shareholder value and executive decision-making. The families of Peter Wilson and Roger Brown received the fine announcement with mixed feelings. Margaret Wilson, Peter's widow, stated $2 million, "That's what they've determined my husband's life was worth to Esso, $1 million. For a company that makes billions, this is pocket change, they'll pay it and forget it. But I'll never forget. My children will never forget." Civil settlements were more substantial. The families received compensation through workers' compensation and civil lawsuits totaling approximately $500,000 per death. Not adequate for a life lost, but significantly more than the token amounts many disaster victims' families receive. John Lowry, the engineer who'd authorized the restart, never faced criminal charges. Investigators determined he'd acted reasonably given available information and had followed procedures. The procedures were inadequate, but that was systemic failure, not individual culpability. Yet Lowry bore psychological scars equivalent to criminal conviction. He left the industry, underwent therapy for PTSD and depression, and struggled with guilt despite being legally blameless. "Everyone tells me it wasn't my fault," Lowry said in a 2005 interview. "The Royal Commission said I followed procedures, the court said I acted reasonably, but I made the decision to restart. I authorized increasing flow through that heat exchanger. Peter Wilson died following my instructions. How is that not my fault?" This psychological burden, carried by individuals even when systemic failures are primary causes, represents a hidden casualty of industrial disasters. Workers who made reasonable decisions within flawed systems carry guilt as if they'd acted negligently. The legal system finds systemic failure, the individual experiences personal failure. The regulatory changes following Longford were comprehensive and lasting. Victoria's Occupational Health and Safety Act, 2004, created new requirements for major hazard facilities, industrial operations where failure could cause multiple deaths or significant community impact. These facilities were required to implement comprehensive safety management systems, audited annually by independent experts. Conduct quantitative risk assessments identifying all potential disaster scenarios, develop emergency response plans coordinated with government agencies and surrounding communities, maintain equipment according to heightened standards with more frequent inspections, train personnel extensively in both routine operations and emergency response report all significant incidents and near misses to regulators. The Act also created provisions for charging individuals, directors, managers, engineers with criminal offenses when workplace deaths resulted from gross negligence or reckless conduct. This created personal accountability that previous laws had lacked, making executives potentially liable for decisions that caused deaths. The gas industry specifically implemented enhanced standards. Restart procedures for plants that had been shut down extended periods were revised, requiring complete instrumentation and monitoring before restart. Slower warming rates with multiple hold points for inspection. Independent review of restart plans by engineers not involved in operations. Higher authority approval for restarts after extended shutdowns. Mandatory waiting periods after maintenance to allow thorough post-work inspection. These changes addressed the specific failures at Longford, but also reflected broader principles that procedures must account for unusual conditions, that production pressure must not override caution, that technical decisions must be reviewed by independent experts. Esso rebuilt portions of Longford with substantially enhanced safety systems. The reconstruction cost exceeded $100 million and took 2 years. When operations fully resumed in 2000, the facility had automated isolation systems that could shut down sections instantly upon detecting leaks. Enhanced fire suppression, including deluge systems and foam generators. Improved monitoring, with redundant sensors and advanced analytics. Blast-resistant control rooms protecting operators from explosions. Emergency shutdown systems with multiple redundant triggers. The rebuilt facility was significantly safer than its predecessor, but it remained a major hazard facility where catastrophic failure was possible. The industry had learned that absolute safety was impossible, only risk reduction and mitigation were achievable. The disaster's impact on Victorian energy policy was profound and lasting. Before Longford, energy infrastructure planning had focused on efficiency and cost. After Longford, redundancy and resilience became priorities. The state couldn't allow critical infrastructure to have single points of failure where one accident could paralyze the economy.